I want you to just do something for me real quick, just for a moment. Try to forget where you are.
Forget the commute.
Right? Forget the commute, the gym, the laundry pile, or your office cubicle. I want you to close your eyes, unless you're driving, obviously.
Please keep them open if you're driving.
Yeah, definitely keep them open if you are behind the wheel. But otherwise, I want you to transport yourself.
We're going on a bit of a trip today.
A very long trip. We are going millions of miles away. You are sitting on a ridge, and you're overlooking this vast, rusty, completely desolate landscape.
It is minus 80 degrees Celsius.
Minus 80. And the wind is just this faint whisper because the atmosphere is so incredibly thin. But the radiation is screaming.
Because you aren't human, you are a robot.
Specifically, you are a Mars rover.
And you aren't just any off-the-shelf robot. You are a absolute masterpiece of engineering. You are very, very expensive.
Billions of dollars of taxpayer money just sitting there on 6 wheels. And you have a mission. It sounds so simple on paper. You need to get from this ridge you're on to a waypoint.
It's about, what, 50 meters away?
Yeah, about 50 meters away. You need to sample a specific rock that the scientists back on Earth are absolutely freaking out about. And 50 meters, it sounds like a walk in the park.
But in robotics, especially space robotics, the word simple is usually a trap.
Exactly. It's a massive trap. Because looking through your camera lenses, the terrain ahead is a total nightmare.
We're not talking about a paved road or a sidewalk here.
Not at all. We're talking sharp, jagged rocks that could easily slash a tire, which, by the way, has actually happened to rovers before.
Real mission killer right there.
Oh, completely. And we're talking about loose gravel that acts like quicksand. And maybe there's a steep drop-off into a crater that you can't quite see the bottom of because the shadows are weird.
This is just an incredibly high-stakes environment. I mean, one wrong move, one little slip on a patch of sand, and the mission is basically over.
You flip over, your antenna points at the dirt, you lose communication, and game over.
So here is the conflict. This is the central tension of our deep dive today. To navigate this absolute death trap, you, the robot, have 2 brains.
Not one. 2 brains.
It's a bit of a split personality situation.
It is. Let's introduce them. Brain A is your fast brain. It's a little silicon chip right there on your chassis. It's snappy. It uses almost 0 battery power.
It's practically instantaneous.
Practically instantaneous.
Yeah.
But, well, let's just be honest. It's a little bit dumb.
Dumb might be a little harsh. Let's call it approximated.
Okay, approximated. I like that better. It's fuzzy. It sees the world in low resolution. It might mistake a shadow for a rock or a rock for a shadow.
It's highly prone to small errors.
It's like glancing at something out of the corner of your eye while you're running.
Right. And then you have brain B.
The slow brain. The absolute genius of the operation.
Maybe this is a massive neural network running on a powerful server back at the base station, or maybe it's even a literal team of human scientists on Earth analyzing your data pixel by pixel.
And it is incredibly precise. It knows the physics perfectly. It can calculate the friction coefficient of the Martian sand grain by grain.
But
there's always a but. It is so incredibly expensive, it drains your battery like crazy to run those calculations. And worse, it's slow.
We're talking seconds, maybe even minutes of lag just to send the data, wait for it to process, and get an answer back.
And if you're actively sliding down the side of a crater, gravity does not wait for you to process the data.
No, it doesn't. You do not have minutes. You might not even have seconds.
So here is the big question. And this is the real hook for today's deep dive for you listening. How does the robot decide which brain to use in the moment?
It can't ask a human for help with the decision. It can't just pause the universe to think about it.
It has to decide right then and there. Do I risk it with the fast, fuzzy brain? Or do I pay the massive cost for the slow, smart brain?
It's the ultimate dilemma of resource allocation. And the fascinating thing is, this isn't just about space rovers.
No, and that's exactly why we're talking about it today. Today we are diving into a really fascinating paper titled Interpretable Trade-offs Between Robot Task Accuracy and Compute Efficiency.
Which is a very, very academic way of saying how to be lazy but smart about it.
I love that.
Oh.
How to be lazy but smart. We're going to call it compute model selection. That's the core concept from the source material. And the mission for this deep dive is to find the algorithm.
The mathematical logic.
Right. The math that allows a machine to perfectly balance being incredibly smart with being highly efficient.
We want the precision of the genius with the speed of the sprinter. We essentially want to have it all.
And before you tune out thinking, I'm not building a Mars rover, I'm just trying to pass my computer science midterms, let's ground this for a second. Why does this actually matter to the listener?
Well, because you are carrying this exact problem in your pocket right now.
Your smartphone.
Your phone, your laptop, eventually your car. Just think about it. You're playing a high-end mobile game. Maybe it's one of those massive open-world RPGs.
The graphics are super intense.
Very intense. Your phone gets hot to the touch. The battery starts dropping, 1% every minute? What is actually happening inside the phone there?
The phone is actively struggling. It's constantly trying to decide how much processing power to use to render the explosions or the lighting.
Exactly. It's making a split-second trade-off. Do I render the shadow perfectly with real-time ray tracing and completely kill the battery in 10 minutes? Or do I give you a blocky, low-res shadow and keep the phone alive for an hour?
Or even something much simpler, like voice recognition.
Yes. Great example. When you talk to a digital assistant on your phone, sometimes it processes right there on the device. That's the fast brain. It's quick, but it might mishear you.
It thinks he said call mom instead of call Tom.
Right. But sometimes, if the request is complex, it actually sends your voice recording to a massive server farm in the cloud to figure out what you said. That's the slow brain.
And that split-second pause where you're just staring at the screen waiting for it to type out the words, that's the trade-off happening in real time.
Precisely. This is the intersection of computer science, robotics, and really economics. It's a literal cost-benefit analysis happening at the speed of light.
So let's get into the actual machinery of this decision. Section 1 of our notes from the paper covers the setup. We really need to understand the tools the robot has at its disposal. The paper uses this phrase, heterogeneous compute resources.
Heterogeneous. It's a good word.
It sounds very fancy, very academic.
It just means diverse or different in kind. In biology, a heterogeneous population just has a lot of genetic diversity. In computing, it means your system isn't just one type of chip.
It's a team.
It's a team of different chips, and they all have completely different strengths and weaknesses.
So who is on this team? Let's meet the roster.
First up, you have the onboard CPU. That's the central processing unit physically located on the robot itself.
The local guy.
The local guy, he's reliable because he's right there. There's absolutely zero travel time for the data. He's hardwired in.
But he's constrained.
Very constrained. You can't put a literal supercomputer on a small drone. It would weigh way too much and require a nuclear reactor to power the cooling fans.
Oh.
So the local CPU is usually weaker, designed strictly for efficiency.
He's the scrappy survivor of the team, runs on IEEE batteries.
Exactly. Then you have the cloud GPU, the graphics processing unit.
The heavy artillery.
Yes. This is located in a massive server farm somewhere else, maybe on a different continent, maybe on an orbiting satellite if you're on Mars.
This is the brain that can crunch a billion numbers in a second.
It can run the most advanced AI models in existence.
Right.
But to use it, you have to package up your data, send it over a wireless network, wait for it to physically get there, wait for the calculation, and wait for the answer to come back.
And that introduces latency. Lag.
Latency and risk.
Yeah.
If your Wi-Fi drops or a solar flare hits your antenna, you are effectively brain dead if you rely purely on the cloud.
And finally, the paper mentions the ultimate compute resource.
Yeah.
The human supervisor.
Us.
The meat bags.
Yes, the biological neural networks. Humans are technically considered models in this framework. We are the oracle for general complex tasks.
We are incredibly adaptable.
Unbelievably so. We can look at a weirdly shaped rock and say, oh, that looks like a duck, which a computer vision system might really struggle with. But we are arguably the most expensive resource on the roster.
Expensive how? Like salary.
Well, yes, but in compute terms, we are slow, we get tired, we require coffee breaks, we get distracted by our phones, and our bandwidth, the speed at which we can actually communicate a complex thought to the robot, is terrible compared to a fiber optic cable.
So the robot has this diverse menu: local CPU, cloud GPU, human. And the paper argues that managing this menu essentially comes down to a trade-off triangle. I love a good triangle. What are the corners?
The robot is constantly juggling 3 balls, and if it drops even one, the mission fails. Ball number 1 is accuracy.
Accuracy.
Yeah.
Makes sense.
How close to the ground truth is your perception? If the camera sees a gray blob, is the robot 100% sure it's a rock? Or is it 50% sure? Or is it literally hallucinating a rock where there is just flat sand? We want high accuracy.
Obviously. We don't want the car to drive off a cliff because it thought the edge was a painted crosswalk.
Ball number 2 is latency, speed. How long does it actually take to get that highly accurate answer? As we said, perfect accuracy is completely useless if the answer arrives 2 seconds after you've already crashed.
Speed kills, but a lack of speed also kills in this context.
Precisely. And bullet number 3 is energy or cost. This can be literal electricity, milliamp hours draining from the battery, or it can be data cost, like bandwidth limits, or even pure financial cost if you're paying Amazon Web Services for server processing time.
It's the classic engineering problem. Fast, cheap, good. Pick two.
That's the old adage. You can have it fast and cheap, but it won't be good. It won't be accurate. You can have it good and fast, but it certainly won't be cheap.
But the whole goal of this paper and the goal of compute model selection is to basically break that triangle. We want to cheat the system.
We want to have our cake and eat it too. We want to find a mathematical way to operate right in the middle of that triangle without sacrificing any of the corners.
So let's formally meet the contenders here. The paper simplifies this whole complex menu into two main characters for the sake of the math. We have fast, the fast model.
Think of the fast model as the intern.
The intern.
Yeah.
Okay, describe the intern for us.
The intern is enthusiastic, incredibly fast, very, very cheap to employ. He's sitting right next to you in the passenger seat of the rover. You hand him a picture and say, "What is this?" He glances at it for a microsecond and says, "Rock." Boom. Done.
Is he right?
Usually. Maybe 80 or 90% of the time he's spot on. But because he's rushing and because he hasn't completed his PhD yet, sometimes he says rock and it's actually just a dark shadow. Or he says clear path and it's a trench. He's running a compressed neural network. He's cutting corners to be fast.
And then we have slow, the slow model.
This is the professor, the Nobel laureate. She lives in a library 3 towns over.
So very hard to reach.
Very. To get an answer from her, you have to physically mail her the photograph. She puts on her spectacles. She studies it with a magnifying glass. She runs complex physics simulations. She writes a tiny dissertation on the geological composition of that specific pixel. And then she mails you back the answer.
This is definitely a basaltic rock formation with a friction coefficient of 0.4.
Exactly. She is almost never wrong. She represents ground truth. But the cost, the time, the effort, the metaphorical postage stamps, it's astronomical compared to just asking the intern.
So the setup is super clear. We have the intern and the professor. We have a robot moving through dangerous terrain. We really need a way to manage them both. We can't use the professor for everything, or we'll literally never get to the destination. We can't use the intern for everything, or we'll drive into a ditch and die. Which brings us perfectly to section 2, the solution. The paper calls this the policy, represented by the Greek letter pi. But I really like thinking of it as the manager. The manager sits right between the robot's eyes and its 2 brains.
Right. It's the ultimate gatekeeper. So visualize the flow of information here. Data comes in. The robot sees an image. Let's call that piece of data X. The first thing that happens every single time is the manager asks the intern, the fast model, "Hey, quick look, what do you think?"
And the intern gives a very quick answer, which we call he fast. He says, "I think it's safe, boss."
Now the manager has to make the critical decision. Action 0, "Okay, I trust you, intern, let's move." Or action 1, "Hold on, you sound a little unsure," or "This situation just looks weird. I'm going to call the professor."
So it's a strict binary choice, trust or verify.
And this is where the paper really introduces the core math. Theorem 1. It frames this binary decision as an economic equation, a pure, calculated cost-benefit analysis.
I love that we're turning robotics into economics. It makes it feel so rational and grounded.
It makes perfect sense, right? Every action you take has a price. The logic is beautifully simple. The manager should only call the professor if the benefit of doing so is mathematically greater than the cost.
Okay, that sounds pretty obvious. If the professor costs $100 to call, but her advice saves me from a $1,000 crash, obviously I call her. That's a net gain of $900.
Yeah.
But if she costs $100 and the worst that can happen is I bump my toe, let's say a $10 cost, I don't call her. I take the hit.
Exactly. That is the fundamental equation at play. But, and here is the massive twist, there's a huge catch to this. A paradox, really.
I feel a plot twist coming.
You, as the manager, know the cost. You know for a fact that calling the professor takes exactly 5 seconds and consumes exactly 10% battery. That's a known fixed number. But how do you know the benefit?
Well, the benefit is getting the right answer instead of the wrong answer.
But you don't know that the intern is wrong. You haven't asked the professor yet.
Oh, I see what you mean.
To know how much better the professor's answer is, you have to know the truth. But if you already knew the truth, you wouldn't need to ask the professor in the first place. You were trying to calculate the exact value of information before you actually have the information.
It's like buying a mystery box.
Uh,
You know the price of the box, say $50, but you don't know if there's a diamond ring inside or just a dead rat until you actually pay for it and open it.
that is the perfect analogy. So how do we actually solve this paradox? Do we just guess? Do we program the robot to flip a coin?
I really hope not. We're building Mars rovers here, not gambling in Vegas.
The solution is what the authors of the paper call the secret sauce, and it relies heavily on statistical correlation.
Break that down for us. What does that mean in this context?
The key insight here is that the intern, the fast model, and the professor, the slow model, they are not strangers to each other. They are deeply related. Usually the fast model is just a dumbed down or heavily compressed version of the slow model. They are trained on the exact same data set.
So they essentially think alike.
They are correlated. Let's go back to the student analogy for a second. Imagine you have a condensed study guide, that's the intern, and a massive, thick textbook, that's the professor. From past experience studying, that the study guide is absolutely great for history dates. It gets them right 99% of the time.
Okay, tracking.
But you also know that for complex physics equations, the study guide cuts too many corners. It simplifies things too much, and it tends to be wrong.
So if I'm the student playing the role of the manager, I'm looking at a test question. If I see it's a history date, I feel totally confident trusting the study guide. But if I see a physics equation, even without knowing the correct answer, I know that the study guide is highly likely to be wrong.
Exactly. I don't know the answer, but I know the probability of the intern messing up this specific type of problem.
That makes so much sense. You predict the error. You look at the situation and say, historically, in this specific lighting condition, with this exact texture of rock, the fast model tends to be off by 20%.
And if being off by 20% is too dangerous for the current maneuver...
You call the professor. You gladly pay the cost.
That's brilliant, isn't it? It's metacognition. It's the machine thinking about its own thinking. The robot isn't just seeing the world, it's actively evaluating its own ability to accurately see the world.
It is. And to make this rigorous, because gut feeling isn't math and engineers really hate gut feelings, the paper uses a very specific concept called core sets.
Core sets. Okay, now we're getting technical. Try to keep it high level for the non-computer science majors tuning in.
I'll try. A core set is basically a compressed version of a massive data set that comes with a hard mathematical guarantee. It's not just a random sloppy sample. It's a very carefully mathematically chosen sample that promises I am never more than epsilon different from the full original data set.
So it's essentially a contract.
Yes, a binding contract. It gives us a hard mathematical ceiling on the potential error. We can actually verify that the fast model is never more than X% wrong compared to what the slow model would say. Having that upper bound is what allows us to write the economic equation.
Yeah.
It turns the mystery box into a calculated risk.
So we aren't just flying blind. We have a literal safety net built directly into the math. We know the absolute worst case scenario of trusting the intern.
Correct. And that worst case knowledge is exactly what lets the manager sleep at night.
Let's look at that math a little closer. Moving into section 3. Now, I promise we aren't going to make listeners solve for X while they're on the treadmill or doing the dishes. But the intuition behind the formula is really, really important to grasp.
It is. The central equation here is the reward function, R sub t of a sub t.
Just think of this as the robot's high score in an arcade game. The robot desperately wants to get the highest score possible. It's gamification of robotics.
Right. So you start with a perfect score. Then the game subtracts points for two specific things. First, you lose points for loss. We call that L.
Loss is basically wrongness.
Yes. How wrong were you? If you thought the rock was a shadow and you drove off a 100-foot cliff, your loss is infinity. Game over. Insert coin. But even if you're just slightly off center while driving on a runway, that's a small loss. We want to keep loss as low as possible.
And the second penalty in this game.
Cost. Little c. Every single time you use the slow brain, you lose points. You spent precious battery. You spent time you didn't have.
So the whole game is be as right as possible while spending as little as possible.
That's kind of the game of life, isn't it?
Too true. But the paper adds a really cool layer of customization here. They talk about these two variables, alpha and beta. These are essentially the knobs the engineer can turn before sending the robot out.
These are the personality settings for the robot.
Exactly. Let's explain alpha first.
Alpha is the heavy weight you put on accuracy. If you set alpha really, really high, you are explicitly telling the robot, I do not care about the cost. I don't care if it takes all day to move 10 feet. You must be right.
Give me a real-world example of a high alpha situation.
A surgical robot. If a robotic arm is cutting into a human spine, you want alpha set to 1 million. You do not care if the surgery takes an extra 10 minutes or uses 5% more electricity. You absolutely cannot cut the wrong nerve.
Right. Safety is paramount. Zero tolerance for error.
Got it. And beta. What's the beta knob do?
Beta is the weight on cost. If you crank up beta, you're telling the robot efficiency is key. We are on a tight budget here, either power or time.
Kind of like a Roomba vacuum.
Exactly like a Roomba. If a vacuum cleaner bumps into your sofa leg because it used a cheap low-power sensor to save battery, it's not a tragedy. Nobody dies. It just turns around and sweeps somewhere else. But if it runs out of battery and dies in the middle of the hallway after cleaning only 3 square feet because it was overanalyzing the carpet fibers with a supercomputer, that's a terrible product. You want high beta for the Roomba.
So this mathematical framework allows us to perfectly tune the robot for the specific mission. We can make a paranoid, careful robot, or we can make a fast, loose, and highly efficient robot just by changing 2 numbers in the code.
Precisely. And the theorem, the core decision rule, just takes these user preferences, looks at the estimated error from the core set we talked about, and spits out a very simple yes or no. Is the estimated danger high enough to justify the cost of thinking harder?
And the authors emphasize one word repeatedly throughout this section: interpretable.
Yeah.
Why is that specific word so important?
This is a massive topic in AI right now. Huge. Most deep learning today is what we call a black box. You feed an image into a massive neural network, and it spits out the word cat. If you ask the network, hey, why do you think that's a cat? It can't tell you. It doesn't know. It's just a soup of millions of decimal numbers that magically aligned.
Which, I mean, is totally fine for identifying cats on the internet, but it is absolutely terrifying for a self-driving car.
Yeah.
Why did you suddenly swerve into oncoming traffic? I don't know. The math just felt good in the moment. Not acceptable.
Exactly. Completely unacceptable for life-critical systems. But this manager system they built is fully transparent. If the robot pauses to use the slow brain, we can look at the data logs later. We can see, the robot stopped because the estimated error bound, that epsilon, exceeded the safety threshold defined by our alpha setting.
We can audit the decision step by step.
We can mathematically prove why it did what it did. That is absolutely crucial for certification. You can't put a commercial plane in the sky if you can't explain to regulators how the autopilot makes decisions.
Speaking of planes, let's actually see this system in action. We've talked a lot of theory. Let's talk practice. Section 4 is Application 1, the taxinet.
Taxinet. This is a very classic visual perception problem in autonomous vehicles.
Set the scene for us. What's the setup?
Imagine a massive commercial airliner. It's not flying. It has landed and is on the ground. It's taxiing from the arrival gate to the runway, or vice versa. But the human pilot isn't steering. The computer is driving the plane.
The goal sounds pretty simple. Keep the front nose wheel painted directly on the yellow center line of the tarmac.
Right. It sounds trivial, but remember, real-world runways are super confusing visually. There are black tire marks everywhere. There are crossing lines from other runways. There are weird shadows cast by other planes and terminal buildings. The input is just a simple video camera mounted on the wing. The output is a steering command, left, right, or straight.
So who are the 2 brains in this specific scenario?
The slow model, the expert professor, is a deep neural network called ResNet 18. It's a very standard industry-grade image recognition model. It's big, it's computationally heavy, but it is very, very good at finding lines in images.
And the fast model, the intern.
For the intern, they used a quantized version of that same ResNet 18.
Quantized. That sounds like sci-fi jargon. Set phasers to quantized. What does that actually mean for the listeners who aren't software engineers?
Think about a digital photograph on your computer. You can have a massive, high-resolution, uncompressed 4K image that takes up 10 megabytes of space on your hard drive. Or you can compress it, you can lower the resolution, reduce the color palette, and make it a tiny, grainy JPEG file that's only 50 kilobytes.
Right. It looks blocky. There are pixelated artifacts everywhere. It's fuzzy.
Yes. Quantization in AI is very similar conceptually. Inside a neural network, the artificial neurons communicate with each other using numbers. Usually these are very precise numbers with many, many decimal places, like 3.14159265. That takes a lot of computer memory to store and a lot of processing power to multiply.
Okay, that makes sense.
In a quantized model, you basically take an axe and chop off all the decimals. You round everything to the nearest whole number, or a much smaller decimal. So 3.14159 just becomes 3. It makes the math incredibly fast because multiplying 3 times 3 is way easier for a chip than multiplying 3.14159 by another huge decimal.
So the model gets physically lighter in memory and much faster to run.
Much faster. In this specific paper, the quantized model was 47% faster to process an image. That is a massive speed boost when you're making split-second steering decisions.
But there's a cost. We established there's always a cost.
There is. The quantized model had a 64% higher loss, meaning it was 64% wronger than the slow model.
Oof. If I'm a passenger on that plane looking out the window, I really don't want the robot pilot to be 64% wronger. That sounds like we're steering right into the grass.
It does sound bad. If you forced the system to use the fast model 100% of the time, the plane would definitely wobble, it would jitter, it might eventually drift off the tarmac entirely.
So they put this manager policy to the test in a flight simulator called X-Plane. They ran 50,000 different images through it. They set the robot's personality to safety first, so a very high alpha. What actually happened?
The results were genuinely staggering. The manager, what they call our selector in the graphs, achieved a 22% higher overall reward than the standard benchmarks. It kept the plane perfectly safe and centered.
But here's the statistic that totally blew my mind when I read it.
Yeah.
How often did the manager actually decide to use the smart brain?
Only 68.6% of the time?
Wait, think about that. So roughly 1/3 of the time, the cheap, pixelated, dumb brain was considered totally good enough to steer a commercial airliner.
Yes. And think about the visual logic of why. A runway is mostly just a long, flat, straight line. It's gray concrete with a bright yellow stripe down the middle. Most of the time, it's not visually complicated at all. You do not need a PhD in computer vision to walk in a straight line.
The blocky, pixelated brain can see a straight yellow line just fine.
Exactly. The manager realized, hey, we're just cruising on a straightaway here. The intern has got this handled. Why pay the massive computational cost for the professor? It only called in the expert model when the plane actually had to make a complex turn, or when the glare from the sun got weird, or when crossing lines made the image confusing.
That is true efficiency. It's not about being the smartest person in the room all the time. It's about being smart when it actually matters.
Selective intelligence, that's the real key to resource management.
I really love that concept. But taxiing on a completely flat runway is one thing. The stakes are relatively low compared to our opening scenario. Let's go back to Mars, Section 5.
The Mars rover simulation, this is the real deep end of the pool for this paper.
They used real terrain data from NASA's IROS program. This isn't a flat runway. This is a chaotic three-dimensional environment.
It is intensely chaotic. You have extremely steep slopes. You have massive rocks that act as hard obstacles, which are the red zones on their map. And the physics of driving are incredibly messy. They used what's called a linearized bicycle model with uncertain dynamics.
Okay, unpack that. Uncertain dynamics meaning what exactly?
Meaning the ground is actively fighting you. It's slippery. You tell the rover to turn exactly 10 degrees to the right. But because of the loose sand or sudden gust of wind or loose rock under the tire, it might slide and actually turn 12 degrees or maybe 8 degrees. You do not have perfect one-to-one control over the vehicle.
This introduces a concept that I found really, really fascinating in the reading, reachability analysis.
Oh, this is a huge cornerstone of modern robotic safety. It's brilliant.
Explain it to me like I'm a high schooler, or maybe a really smart 12-year-old.
Okay, I can do that. Traditional navigation just asks, what is the path? It draws a single clean line from point A to point B. It fundamentally assumes you will follow that line perfectly.
Like GPS on your phone.
Right. Reachability analysis asks a much harder question. It asks, given the uncertainty, given that I know I might slip or skid, what is the entire set of all possible physical locations I might end up in over the next 5 seconds?
So it's not drawing a line, it's drawing a shape, like a cone spreading out in front of the car.
Exactly. It's computing a cloud of possible futures. It says, if I hit the gas right now, I might end up exactly here in the center, but I also might end up way over here to the left or way over here to the right.
And if any tiny part of that expanding cloud touches a rock,
you are deemed unsafe because there's a mathematically non-zero chance you will crash into that rock. Even if the dead center of the cloud is completely safe, the blurry edge of the cloud might kill you.
So applying our framework, we have two brains again. The fast reachability and the slow reachability.
Yes, the fast reachability is a very quick, dirty sketch. It just draws a rough, simple circle around the robot. It's incredibly fast to compute, but it has low confidence. It might be too small of a circle. It might completely miss a potential skid trajectory.
And the slow reachability.
The slow reachability runs thousands and thousands of Monte Carlo statistical simulations. It simulates every single grain of sand to build a high-fidelity, highly precise, weirdly jagged shape of the true future.
But running thousands of simulations drains the battery and takes forever. So how does the manager decide which one to use? This brings us to what I think is the absolute coolest strategy in the whole paper. Bloating.
Bloating. It sounds very unappealing. Makes me think of eating way too much Thanksgiving dinner. But in the world of robotics, bloating saves lives.
Visualize this strategy for us.
Okay, imagine the fast model draws its rough, simple circle of where the robot might go. We know for a fact that circle is probably wrong. It's too tight. It's overly optimistic about how much control we have.
Okay, I'm picturing a tight circle.
So the manager policy applies a mathematical factor. This is based on that epsilon error bound we talked about earlier. And it explicitly expands the shape. It blows the circle up like a giant balloon. The formula they use is essentially expanding it by a factor of 1 over 1 minus epsilon.
So it intentionally makes the circle much bigger than it actually needs to be.
Yes. It creates a massive worst-case scenario bubble. It mathematically says, okay, even if the fast model is wrong by the absolute maximum possible amount guaranteed by our core set, the robot will definitely, 100%, be somewhere inside this giant bloated bubble.
I see. It's exactly like parking your car. You know your car is, say, 6 feet wide, but when you're squeezing into a tight spot between two expensive cars, you mentally pretend your car is 8 feet wide.
That is exactly it. You purposefully leave a massive buffer. You assume you are way clunkier than you actually are.
So if I pretend my car is 8 feet wide and I still easily fit into the parking spot without touching the lines?
Then you know for an absolute fact you won't scratch the paint. You don't need to get out of the car and measure the distance with a tape measure. You don't need to invoke the slow model. You are safe by a huge margin.
That is the trick. If the bloated fast set does not hit a red rock on the map, the robot just keeps moving. It totally trusts the intern because the intern's worst-case guess is still provably safe.
Exactly. But what if the giant bloated balloon does touch a rock on the map?
That's the trigger point.
The robot says, whoa, hold on. My rough expanded estimate says I might crash. Now, it could be a real, actual crash trajectory. Or it could just be that the balloon is way too big and the actual physical path is completely clear.
But the robot doesn't know. The fast brain isn't sharp enough to tell the difference. So it calls the professor.
Right. It says, hey, professor, can you please run the heavy physics simulation? Am I actually going to hit this rock, or am I just being overly paranoid with my buffer?
And the slow model runs the heavy numbers. It shrinks that giant balloon down to the precise, jagged shape of physical reality. Usually, it turns out the path was safe all along and the bloated bubble was just being paranoid. But sometimes it confirms the real danger and the robot hits the brakes or steers away.
This dynamic switching back and forth is visualized so beautifully in the paper. If you look at Figure 4,
Describe Figure 4 for the listeners.
you see a top-down map of the Martian terrain. There are red zones marking all dangerous obstacles. The rover's path is drawn as a colored line. When the rover is in the wide-open sand, the easy flat terrain, the path is colored blue. Blue means it's running purely on the fast brain. It's zooming along. The bloated box is huge, but there are no rocks around, so it hits nothing.
So blue means fast and cheap.
Then the path snakes into a narrow gap between two big red rocks. Suddenly the line turns green. That green is the slow brain. The manager realized the giant bloated box was brushing against the rocks, so it instantly switched to high precision mode to safely thread the needle.
And once it gets through the narrow gap,
It turns immediately back to blue. It accelerates and goes back to being cheap.
that is exactly how a human drives. When we are on an empty highway, we zone out. We use our fast brain. We listen to a podcast. We look at the scenery. But the second we see brake lights ahead, or we enter a tight construction zone with orange cones,
We lean forward, we physically turn down the radio, and we focus. We activate our slow brain.
it is exactly the same thing. It is situational awareness. It's dynamic resource management adapted directly to environmental stress. And what were the final results of the Mars simulation?
Unbelievable. The rover never hit a single obstacle. 0 collisions. Total safety. But It completed the complex course much, much faster and with way less battery than if it had just used the slow policy the whole time.
Let's look at the final scoreboard then. Section 6, Evaluation and Results. We need to compare our selector, this manager we've been talking about, to the standard competition. Who did they race against in the simulations?
They had 3 main rival benchmarks. First up is the fast policy. This is the absolute daredevil. It uses the cheap intern brain 100% of the time, no matter what.
And the result for the Daredevil?
It's very cheap, super low cost, but on the messy Mars terrain, it crashed. High error, total mission failure.
Like second contender.
The slow policy.
Yeah.
The absolute perfectionist. It uses the expensive professor brain 100% of the time.
Result?
Perfect safety. It didn't crash once, but the cost was absolutely sky high. In a real-world mission, this robot would literally run out of battery halfway to the destination, or it would move so painstakingly slowly that the mission timeline would expire before it ever got the rock sample.
Third contender.
The random policy. Literally flick a coin. Heads, I think fast. Tails, I think slow.
I assume this was completely garbage.
Total garbage. It's the worst of both worlds. It blindly spends expensive compute on the easy, flat parts and randomly uses the dumb brain on the hard, dangerous parts. It has zero context.
And then they mention one more benchmark.
Right, the Oracle. This is a purely theoretical benchmark. It's basically a cheat code. Imagine a magical robot that can peek into the future and know exactly when the fast model will be wrong without ever actually paying the computation cost to check.
But that's physically impossible. You can't know the error without calculating the truth.
It is entirely mathematically impossible, but scientists use it because it gives us a firm ceiling. It tells us the absolute maximum possible score a perfect algorithm could ever achieve.
So how close did our manager actually get to this impossible oracle?
In the TaxiNet runway experiment, it was within about 10% of the Oracle's performance. It was performing almost as well as a literal psychic robot.
That is incredibly impressive.
And in the mathematical linear regression tests they ran, it achieved a 245% higher reward than the other standard baselines. It didn't just win the race, it completely lapped the field.
There's a graph in the paper, figure 3, that really sums this up visually for anyone who likes charts.
Yeah, imagine a scatter plot graph. The x-axis along the bottom is cost, battery drained. The y-axis going up is error, or loss.
Okay, got the picture.
The fast policy sits way up in the top left corner, very low cost, but very high error. Bad place to be.
Right.
The slow policy is way down in the bottom right corner, very low error, but incredibly high cost. Terrible efficiency.
And ideally, we want to be right there in the bottom left corner. Low cost, low error.
And that is exactly where our selector, the manager, sits on the graph. It dives right into that sweet spot. It effectively manages the trade-off that everyone else previously thought was basically impossible to break.
So zooming way out from all the math, what have we really learned here today? We've talked about epsilon bounds, core sets, bloated sets, taxi nets, but what is the big grand takeaway for the listener?
The biggest takeaway is that artificial intelligence isn't just about raw processing power anymore. It's really about management.
You don't necessarily need a bigger brain. You just need a much better boss.
Exactly. We so often think that better AI just means a bigger neural network, more parameters, trillions of parameters, massive server farms. But this paper mathematically proves that you can build a vastly smarter, safer system just by knowing precisely when to use the dumb, cheap tools.
It all comes back to the power of correlation.
Yes, deeply understanding that your quick, dirty sketch is statistically related to your final masterpiece. If you can mathematically model your own ignorance, if the machine can confidently know when it is likely to be wrong, it becomes infinitely more efficient.
It's interpretable, it's provably safe, and it's highly economic. Where does this technology actually go next? What's the future application?
Swarm robotics. This kind of math is the absolute future of swarms.
Explain how that connects.
Imagine a massive search and rescue mission. A building has collapsed. You want to send in 1,000 tiny drones, roughly the size of bees, to map the rubble and find survivors.
Hey, I can picture that.
You physically cannot have 1,000 tiny drones all simultaneously streaming 4K video back to a cloud server at the exact same time. The wireless network would instantly crash. And obviously, you can't put a heavy supercomputer on a plastic bee.
So they have to be able to think for themselves locally.
They desperately need this exact logic. They need to fly around using their dumb, fast brains 99% of the time just to save their tiny batteries and save network bandwidth. They should only ping the cloud or use heavy compute when their fast brain sees something that actually looks like a human arm or a face. This math is the literal key to making massive swarms computationally viable in the real world.
It effectively decentralizes the intelligence. It pushes the hard decision-making all the way out to the edge of the network.
Precisely. And because it's interpretable, it builds human trust in the system.
I want to leave the listeners with a final, slightly mind-bending thought before we wrap up. The paper specifically mentions a limitation of their current model. They call it action independence.
Ah, yes.
Yeah.
The fundamental assumption that time just stands still.
Right. In all of these models we discussed, the Mars rover, the taxiing plane, we implicitly assumed the robot could just pause, run the calculation of should I use brain A or B, and then act. We assumed the physical world politely waited for the decision to be made.
But out in the real physical world, the clock literally never stops ticking.
Exactly. Imagine a high-speed racing drone flying through a really dense forest at 60 miles per hour. A massive oak tree is coming up fast. The drone thinks, that shape is a little ambiguous. Should I use my slow brain to carefully analyze it?
If it takes even 0.5 seconds to boot up the slow brain and make that decision.
It has already traveled 15 meters forward. It has already smashed into the tree.
Exactly. The actual physical act of thinking is a real action. Thinking consumes time, and when you are moving, time is literally distance.
So the decision to be careful and use the slow brain might actually be the exact thing that causes the crash, simply because being careful is too slow.
That is the very next frontier of this research. Factoring in the cost of computation, not just in terms of battery energy or cloud data, but in terms of physical survival in a moving environment. The robot has to instantly decide if it even has the physical time to think about thinking.
It's getting incredibly meta.
It's turtles all the way down from here.
Next time you see a spinning loading circle on your phone, or you're playing a game, and you see a texture suddenly pop from blurry to super sharp, I really want you to remember this conversation. There is a tiny, incredibly stressed manager inside that silicon chip, frantically doing high-speed economics, trying to save your battery life without you ever even noticing.
It's a very busy, very math-heavy world in there.
Thanks for taking this deep dive with us today.
Always a pleasure to be here.
Stay curious, everyone. We'll see you on the next one.